We talked about wireless, but now let's talk about wired transmission media, specifically copper cabling and fiber optic cabling. So let's talk about copper, the cabling, the connectors. Then we'll move on to light to carry data, fiber optic cabling and connectors and transceivers, then media converters and SAN connectivity, and then we'll have some review. So starting with copper cabling. Once upon a time, the IEEE, the Institute of Electrical and Electronic Engineers, in the second month of 1980, 802, had sort of a conference, and they had these different little committees, and they had each committee hive off and generate standards. So when you hear 802 this and 802 that, that points back to that. Now, many standards have come about much later than that original conference, but we still refer to them as the 802 standards. Well, the group that worked on Ethernet worked on the 802.3 standards. So Ethernet, back in 1983, Ethernet was standardized to 802.3, and the original called for coax 10 base 5, which was also known as thicknet, and 10 base 2, also known as thinnet. So that was original Ethernet and LANs. Then we moved on to 1995, 802.3U for twisted pair for 100 megabit or 100 base TX. Now, when we say things like 10 base T, 100 base T, 100 base something, gigabit or 10G base or 1000 base, what we're talking about 10 or 100 or 1000 or 10G, that's the speed. And then base means baseband. The signal is put straight on the media without piggybacking on top of a carrier frequency. So it's baseband as opposed to broadband. And then the -TX, SX, SR can stand for different things, like short range, long range, twisted pair, whatever. So 802.3U introduced 100 megabit twisted pair, 100 base T, for fast Ethernet for enterprise networks. Then in 1999, we got to 802.3Z or AB. That's when we introduced 1000-based, wow, gigabit for data centers. And then a little bit later, AE for 10 gigabit, and then BA for 40 gigabit and 100 gigabit, and it went on and on and on. So there was 802.3CD in 2018, 200 and 400 gigabit. Now you'll notice that we started out going over coaxial cable, then we went to twisted pair, and then we went to fiber from that point on. So we have a whole bunch of standards here. Will you need to memorize these particular standards for the exam? Probably the ones regarding power over Ethernet and maybe some of the more recent ones. But every single one to the smallest detail, probably not. So let's start with something we've all worked with many, many times, unshielded twisted pair, or UTP. So you've got in this PVC plastic jacket 4 pairs of wires that are twisted around each other. And the reason for the twists is because, well, there's a physical reason, but if like a burst of radio frequency interference or electromagnetic interference cuts across these, they come to a differential amplifier at the end, and the twists make it easier for them to reject that spurious noise that cuts across both, because the 2 wires twisted around each other are 180 degrees out of phase with each other, but the burst of noise will come in with the same phase, so it's easy for the differential op amp at the end to just reject anything that's not a balanced signal. So that's the whole concept behind UTP, and I apologize if I spoke Martian for a moment there. You don't need to memorize that, but that's the concept behind it. And the more twists per foot, the more impervious that cabling will be against EMI and RFI. Now, however, it's still not great. So I have this story. These guys in a military hospital, they came up to me one time, they said, man, we're having so much trouble. We've got so much, noise on our network, and just the performance is terrible, and there's lots of loss and blah, blah, blah. And I said, well, describe to me your network. Well, it was all unshielded twisted pair, and some of it went through their radiology department. And I'm like, guys, you do realize that an MRI room is Faraday cage shielded. The whole room is encased in copper sheeting. You don't see it because the walls are in front, but you can't run twisted pair through something like that. You're going to either need to route way around it or put fiber optic through there. So anyway, I had to kind of explain to them the physics and the mechanics of why twisted pair is not good in a high noise environment. And when I say noise, I don't mean people shouting, acoustical noise. I mean EMI, RFI type noise. But anyway, unshielded twisted pair, it's the most common kind. This is a close-up look of it. And you can see there's an orange pair, a green pair, a blue pair, and a brown pair. And we'll get to this wiring standard and the pinouts shortly. So this is the most popular type of network cable used everywhere. It's inexpensive, it's easy to install. It has an IEEE recommended maximum distance of 100 meters. Now, let me tell you the secret about cabling and distance, okay? This is an IEEE recommended maximum because past 100 meters under reasonably good conditions, you're going to just have too much signal degradation because over a length of time, or length of space rather, over cable length, the signal is going to get weaker and weaker and weaker. Now, it is true that you will see lower grade cable in like a telephone room, lower grade cable in very, very short distances, like 10 feet or 20 feet, that are carrying higher data rates, but since the distance is so short, it's okay. So that's the sort of the general thing here. This is the recommendation when you're throwing network cable. Now, if you've got electromagnetic or radio frequency interference coming along, that 100 meters may get shortened down, especially when you're dealing with things that are like access points and cameras and power over Ethernet devices. They require a little bit more fidelity. So you might have to use higher grade cabling or just try not to have it so far away. Anyway, unshielded twisted pair, IEEE recommended max distance 100 meters. Higher speeds might have shorter distance limits. Any cable that's going to carry power over Ethernet is going to have distance limits because it's going to use some of the wires to carry DC, and DC will also get drop off. The voltage it'll have a voltage drop, a steady voltage drop the farther down the cable you go. So the general rule of thumb, unless the conditions are bad, you should be repeating that cable. You should have a repeater, just a hub or a switch. You should have it before 85 meters to keep that thing going. We use unshielded twisted pair in Ethernet LANs, and we use them mostly in offices. Now here's shielded twisted pair, STP. It's like unshielded twisted pair, although we started doing shielding with higher grades of cable. But you can see that it will either have a foil wrap, and sometimes it's a braid, around all of the pairs, or each pair will have its own little foil wrap, and sometimes you have both. And the whole idea is that along with this, there's a drain wire. I don't know if you can see it too well, but the drain wire will help collect any spurious noise trapped by that shielding and shunt it to ground. So this is shielded twisted pair. It wraps the wire pairs in a conducting foil shield to reduce electromagnetic interference. It's good for areas of higher RFI, radio frequency interference, or EMI, electromagnetic interference. Not completely impervious. You want completely impervious? Use fiber optics. It is thicker and more expensive than UTP, obviously. Here's a little picture of a direct burial capable Cat6A. It means you can actually take the cable, besides its normal PVC outer, it has like a thick rubber additional outer jacket, so you can directly bury it in the soil. And I've done that plenty of times to trench a cable across a parking lot or just across a walkway or something like that. You might also choose to, instead of having direct burial cable, you might choose to just have a good PVC pipe that you pull the cable through. Just make sure no water gets in. Otherwise, you're going to want to use something with that direct burial capability. You're going to need to memorize at least some of this table, the twisted pair cable categories. Now, first of all, twisted pair cable, the little wires inside should be copper. I have seen cheap versions where they used some steel or something, or aluminum. No. Should be copper. But anyway, here are the cable categories. Let's go over them. Cat 1, that's just telephone wire, really. Can handle up to 1 megabit per second. You know, you'll still see Cat 1 phone wire. Cat 2, this was back in the old token ring days, and I don't think anyone does token ring anymore. This is where we actually started using it for Ethernet. Cat 3, 10 megabit Ethernet. Cat 4, that was when token ring tried to compete with Ethernet. It got as fast as 16 megabits and didn't get any faster. Cat 5 was really cool because now we're at fast Ethernet, 100 megabit. And then, how cool is this? Cat 5e and Cat 6, two competitors, both did gigabit Ethernet. 5e was cheaper, so you couldn't go quite as far, had to have it in really good environments, but it was a lot cheaper, 5e. But Cat 6, under certain conditions, 55 meters, a lot shorter, like only half, you could get up to 10 gigabits. Then we had 6A, where you could truly get up to 10 gigabits at that 100-meter distance. Now, there was a non-standard version called 6E. It's not standardized, but it is for up to 10 gigabits per second at 100 meters. In fact, I was creating some cable harnesses with some folks just the other day using 6E riser cable. So then there's, let's see, we have Cat 7. Cat 7 was developed for something specialized, something called Stream Control Transport Protocol, SCTP, which is for managing like phone calls. It's a call carrier control purpose for up to 100 meters. It wasn't widely adopted, but you'll see it in telcos. And now we have Cat 8. It can go up to 40 gigs, but short distance right now, 5 to 30 meters. You probably should memorize from Cat 5 up to Cat 8. Here is just a look at what some of these common ones look like. Good old 5E, twists, no shielding. You know you're dealing with 6, at least 6 and 6A and 6E, because you'll see like a little plastic divider. It's got it's like a little cross-shaped thing, and it's got 4 little sections or 4 little spots in it, and each pair goes in there. So that's how I know I'm getting 6. The original 6 was not shielded, but 6A, as you can see, is. Then 7 had not only shields for each pair, but also a foil braid around it. And then you can see 8 is like that too, but the braid is nicer. So just looking at these and just kind of recognizing them just visually. So now let's talk about plenum versus non-plenum grade cable. You know, every now and then there will be a building fire, hopefully none of the buildings you ever work in, but when that happens, stuff burns, and when stuff burns, it gives off smoke. Well, the problem with cable for like Ethernet, networking cable, is that the cheap stuff, and I don't mean it's the bad stuff, but the cheaper stuff is not created specifically for a fire situation. So there's this sort of specification called plenum. Plenum is a classification based on fire safety, not the actual cable type itself. Plenum grade cable, and this can apply to twisted pair, coax, or fiber optic. Plenum grade cable has a plastic jacket that will give off very low smoke, or at least very low toxic smoke. That's plenum grade cable, as opposed to non-plenum grade cable that gives off toxic smoke when it burns. So the idea with plenum grade cable is if you're going to pull the cable through the ceiling, and so many buildings, the ceiling is a massive air duct return space for all of the air, that's piped in, and then it returns through the ceiling. That is called the plenum. Well, if there's a fire, what you don't want is that cabling within the air return giving off toxic fumes, which is then going to be spread out across the entire building. So you want to put plenum grade cable in there that minimizes that risk. Now, if you're pulling cable in areas where air return is not going through, like the wall or the floor or something like that, then you can use the non-plenum grade all you want. So anyway, you have the plenum grade, shielded or unshielded twisted pair or fiber optic cable or coax or whatever. Put it in the air ducts in the plenum spaces as opposed to the non-plenum. Put it in walls, floors. In terms of fire safety, plenums is, much more expensive, but it won't kill people with the toxic fumes. And it will have specially treated plastic for its outer jacket. And of course, it's more expensive. Now we're talking about coax, coaxial cable, and we still have that. I mean, we have coax for like cable TV and cable modems. I mean, my ISP is a cable provider, so I have coax coming from them, which goes into a router which has Wi-Fi and a few Ethernet ports. Well, coax, as we saw, 802.3, was the original standard for Ethernet networks. You have a single core, and that's usually a solid core, although there are some cases where it can be stranded, twisted together. And then you'll have an insulation around it, and then you'll have some kind of braided shield. And then it'll have like an outer jacket. Now, the shield, to be data grade, should have a 95% braid or more, so that it's not like big gaps inside of the weave of the braid. I have seen some coax with a stranded core. Most of it has a solid core. It really kind of depends. But you want it to all be copper. You don't want to have like other metals in here. It's just not as high quality. Here are the different coax cable types. Now, one of the things about coax, and this is true really of any conductor, is that they'll have what's called an impedance. Impedance, the short answer is it's resistance to alternating current. There's a little bit more elegant definition of that, but we don't need to go there right now. Coax generally comes in either 75 ohm or 50 ohm impedance, and you need to make sure that the coax you use matches the application, because if you have a transmitter and it expects 75 ohm coax, if you put something different, you're going to get reflections, and it's going to be hard on the transmitter, and the transmitter will probably overheat, and you'll have signal degradation and signal loss. So there are different kinds. RG6, if you still get cable TV and cable modem, that's what you're going to see connected. RG6, it's probably this stuff right here. The old RG59 was used for 10^2 for thin net. We don't use it for that so much anymore, but we do use it for closed circuit analog cameras, as well as short range audio video connections. We might have something called RG11 for long distance cable TV or backbone connections. Ham radios will use RG8. And then there's something called Lockheed Martin, which is 50 ohm for specialized military and aerospace applications. Do you need to remember these standards? Probably not, but you need to understand that there are different types of coax cable and that they have different applications. So now that brings us to something that you're going to see a lot in data centers, something called twin-ax or twin-axial. And I use twin-ax all the time. This is like coax. You can see it's kind of like coax, but instead of a single core, it has two stranded cores inside, and they're twisted around each other. So it's kind of like twisted pair, but really thick, strands, not just single cores. They're twisted, but then they're encased as if they were coax. And so they use not only the shielding from the coax, but also the twists for differential signaling, which rejects, like I've described before, rejects EMI and RFI. So they're really good at rejecting noise, and they have really good data integrity. And use them, I mean, they're typically like 10 gigabit, but they're not very long. They usually are like 5 meters or so. And usually, yeah, it's 5 meters, I think, is the max. But if you amplify them, you can squeak it up to 7 meters. But that's perfect for small data centers. I mean, it's just, or like connecting racks together, what we call top of rack. So it's really excellent that way, and it's a lot cheaper than fiber optic. So the shielding and the twists both help reduce the EMI. You can go 10 gigabit, 400 gigabit if you want, but can't be very long. The cable can't be very long. It's used in the vast majority of what we call direct attach cables, DAC cables. I'll show you in just a sec. So here we are, 1 sec, less than a sec. DAC cables usually are made of twin-X, and they'll have specialized sort of SFP transceivers connected to them, already connected. You don't like plug them into a connector. So these things, it's a complete cable with transceiver assembly, and they'll take Ethernet up to 400 gigabits per second, depending upon the kind of transceiver and the kind of port you're plugged into. Like I said, typically the cabling itself is twin-X. It's pre-assembled, factory terminated, and it'll have different kinds of transceivers. We'll talk about the different kinds, SFP plus, quad SFP, or quad SFP 28. We'll talk about those in just a moment. And it is a lower priced alternative to fiber optic cable. So I use DAC cables all the time in small environments, small data centers. Like I said, it's commonly used top of rack, end of row, meaning you have racks connecting to each other. And we use it to connect servers or switches and storage in the same or a neighboring rack. So let's talk about all those copper cabling connectors. You must know this one, right? The RJ11. This is what we use for phone lines, landlines. Does anyone still have a landline? But this is it. It's got 4 little wires, 4 little pins. I mean, that's like a big blow up of it. And it's usually flat cable, although, you get Cat 1. It'll come just like in one jacket with 4 wires. But this is the pin out. So you have 4 pins, but for the most part in landline telephones, we just use red and green in the middle for line 1. If we're using black and white, we're either using it for the old Princess phones that had the little light on them, the older phones that had power, or if there's a second line, or mostly it just goes unused. Now here's the one that you're going to see everywhere. That's the RJ45, the registered Jack 45. We use it to terminate pretty much all untwisted and shielded twisted pair patch cables. It's got 8 pins. 4 of the pins are for sending and receiving data. The other 4, you could have them carry power or do something else. You will need to know these termination standards. Not only in real life are you going to need to crimp these. I mean, prefer to use factory created if you can. But there will always be situations where you have to custom make a cable, or you have to make a cable real quick. You need to know these standards, all right? So just remember them. There is something called EIA-TIA, which I can't remember what it stands for. You don't need to care. There's version 568A and B. In most cases, straight through normal patch cables, like from your computer to the wall or from a switch to a patch panel, those use TIA 568B. You can use A, but most people just use B for whatever reason. Memorize this, okay? Pin 1. So when you are looking at the underside of a cable, let me just grab an example here. So I've got this, and I've got this little cable here, and so I'm going to look at the underside of the cable where I can see the little pins. When I'm looking, pin 1 is always on the left. So it's pin 1, when you're looking at the actual little wires here, pin 1 is always on this side, left when you're looking straight at it. And pin 8 is on this side, okay? Pin 1 is going to be white-orange, followed by orange, followed by white green, that's pin 3, followed by blue, then white blue, that's 4 and 5. 6 is solid green, 7 is white brown, and 8 is solid brown. That's the B version of the standard. The A version of the standard flips the greens and the oranges. Now, there is some significance to that, which I'll get to in just a sec. You might think, that's really weird. I don't really follow the logic. Look at it from a different perspective. Look at it on how the pins are paired up. If you look at A or B, you'll notice that the first two pins, pins 1 and 2, are one pair. And then the middle pins, 4 and 5, are another pair. And then on either side of 4 and 5 is another pair. And then way down at the end is another. So if we look at it from a different angle, like we look at the B version from this angle here, pins 1 and 2 are the oranges, white, orange, orange. Jump to 4, 5, the blues, but they're reversed. Blue, white, blue, not white, blue, blue. Blue, white, blue. Jump to the last pair, 7 and 8, white, brown, brown, and then 3 and 6 are the greens. A, same concept, but just the greens and the oranges trade places. So that is another way of looking at the wiring for RJ45. Okay, now like I said, most straight-through cables implementations use 568B. You don't have to, but most of them do. If you need to make a crossover cable, and I had to 2 days ago, I needed to make like a 30-foot long crossover cable. Put 568A on one side and 568B on the other, and ta-da! You have your crossover cable. Now, mark it so everybody knows. If you go to a store and you buy them, usually crossover cables are orange in color, just so everyone knows. But just mark it. So please remember this wiring, because you will be expected to look at it and say, I see what the problem is. This is why it's not working. So just warning you. And also in real life, although we try to buy pre-made, factory-made cables, it doesn't always happen. So now you've probably seen this all over the place, the F-type connector, okay? This is the kind where usually you just push it on and then you turn this nut to like tweak or to clamp it down, right? So this is what we use for regular coax, cable modem type connections. So if you have cable TV, cable modems, we use F connectors for those. So it's a coaxial RF connector used for TV, either on land, on Earth, or cable TV or satellite TV or cable modems. It uses RG6U cable, or the older installations might use RG59U cable. You push the connector on and then you turn the nut and it screws in to hold the thing in place. Then we have the BNC connector, and it actually stands for Bayonet Neil Conselman, although lots of folks, myself included, call it the British naval connector. That isn't really where it came from, but I guess that kind of held, even though it was named after the people who designed it. I think British naval connector came about because that was where it was used a lot. Okay, whatever. Anyway, BNC, it twists to lock. So it has a quick twist lock design, and it's used to terminate coaxial cable. You can get 50 or 75 ohm versions. Common uses besides coax, the rubber ducky antennas for handheld radios. Take the antenna on, or take it off, put it on. Analog closed circuit TV cameras, or when you go into professional broadcast or video studio, they will use coax to carry high-speed video. They call it an SDI cable. And there are some test measurement instruments, like you'll get oscilloscopes and things like that, where like the probe will use a BNC connector, or aerospace military applications. If you look really closely here, instead of just a raw wire being the center pin, there's actually a little like gold-plated pin that's crimped onto it. I remember putting these together. You had to like crimp the pin on and push the whole thing through and then crimp the outer thing, and yeah, tiring on my hand. So now let's talk about using light to carry data. So light, and it can be LED light, but mostly it's laser light these days. Light, just like radio, can carry data. It can be the base signal, or it can be the signal, the channel, that is then modulated, modified to carry this voice video data on it. So when we modulate a carrier frequency, we are piggybacking the actual signal that we want onto it. Light can travel along a variety of transmission media so long as they're kind of clear. So optical fiber, air, water, space, we know light travels through space. So light will also bend with the transmission media. And you see here in this picture, this is actually tubing. And we've got a little light source here, and the tubing is carrying the light round and round and round until it finally comes out here. Even though light beams initially, well, depending, light beams kind of go in one direction, but if the light is not a laser, if it's not what we call coherent, it just like has all these little individual rays that go all over. But the nature of light, and in some ways sound is kind of like this, is such that when it hits whatever media it's traveling along, bends or curves, the light will reflect inside of it. It's actually, there's a scientific name for it called total internal reflection. It's based on the refractive index of the conductor and then something outside of it. And I'm not trying to teach physics, but if you want to look that up, you can. The idea is that the light is going to go through here. If it hits the boundary between the two materials, like in this case, the tube and air, if it hits it at a steep enough angle, it'll bounce back into the carrier material rather than just like shooting out. I mean, some of it does escape. This is not unlike, have you ever been like in a place where there's a pool table or a billiards table, you took a ball, and you can either like send it straight down the middle, right? Or you can send it off to the angle and it bounces as it goes down. Well, it's kind of like that. So the two materials could be water and air, plastic tube and air, or optical fiber, and it's cladding, and I'll show you in just one sec. So it's this principle of total internal reflection, which is basically a differential between the refractive indexes of the conductor and the thing around the conductor. That's what makes fiber optics possible. It makes it possible to bend light along the path of whatever's conducting it. So here's an example here. Here's like a plastic bottle with a hole in it, and you can see water's kind of coming out of the bottle, and they shot a laser from behind. You'll notice the laser isn't just coming straight this way. It is staying with the confines of this tube of water, so to speak, this stream of water, because there's a refractive index difference between air and water, so you get that total reflection thing. The laser beam will stay trapped inside the water stream because it bounces off the edges of the stream instead of just escaping out. Fiber optic cables will do the same thing. Light will travel by reflecting off the inner walls and staying in there. This allows the cable to bend and curve and whatever, and the light will stay with it instead of just shooting out. Now, if the cable's damaged, if you have the bend, most fiber optic cable has what's called a bend radius, where you shouldn't bend it any sharper than that, any harder than that, because it exceeds the bend radius and light will start to escape out. You'll see areas that will start to glow. So, you might have light leak out at that point. So let's talk about carrying light on optical fiber. Now, optical fiber is a long, really thin strand of glass. Yeah, glass. About the diameter of a human hair. Ooh, that's really thin. And you might think glass can't bend. Well, when it's that thin, yes, it can. So it can bend. Now, if you've ever taken a class, some of my colleagues, to tip fiber, as we call it, we're very careful because you'll be cutting off tiny little fragments of glass. It's easy to inhale them. You don't want to have any food or drink nearby. We tend to use some electrical tape when we're doing stuff to trap any little stray pieces, because you don't want one of those sticking in your finger. It hurts, and it's really hard to pull out. It's not tough like a sliver. Anyway, through a special manufacturing process, the optical fiber is really thin and long, and it will carry the light. So this core fiber will be surrounded by an outer layer called the cladding. Cladding will have a different refractive index from the core. So that means when the whole thing bends, because of the difference, it creates something similar to a mirror effect where the light will just stay within the core and bend with it. And that's the whole concept here. So the light reflects off the core walls. It bounces its way down the fiber until it reaches the end of the cable. Now, when we carry light down fiber optics, we have two kinds of modes, and it has to do with whether or not you have a single beam or multiple rays. So multi-mode is where the thing generating the light does not create one single frequency strong beam. Instead, it will create many weaker rays of light, and I'm going to show you in just a sec. And these multiple rays, also known as modes, travel down the larger core, and they travel at different angles, so they reflect at different points. Because of the total internal reflection, the refractive index, the rays are reflected from the cladding back, and they stay in the core all the way down. But the problem is, and you've seen this if you've ever done this with a pool ball, if you are bouncing too much, you will quickly lose energy, and your ball might never get all the way down to the end. So the problem with this multi-mode, because you've got individual little tiny rays, streams of photons kind of going at different angles, even though they're all together carrying the signal, and basically it's a bunch of weak rays together carrying a signal, you go too far with that, they'll become so out of phase with each other and arrive at different points in time, and just the signal is just too distorted. So it's really only good for shorter distances on a practical level, but it's a lot cheaper. Single mode is where we will generate a stronger single frequency, well, as close as we can, beam of light, and it'll travel through a much smaller core. There's less need for reflection. There's one beam. The degradation of the signal is not as fast, so we can go a lot longer. So I promised I'd tell you how it is that with multi-mode light that we don't have one single source. Well, here it is. There is a very common way of generating multi-mode light called the V-cell, or V-cell really. It's the vertical cavity surface emitting laser. What it is, and this is kind of like a picture of it, it's a little inky-dinky rectangular grid, and there are these little surface laser elements that will together create a beam, and well, they'll each create their own beam. The problem, of course, is that you've got multiple beams of light. You didn't need a whole lot of power. Okay, that's the beauty of it, because generating laser light actually requires a lot of power. But these V cells, they create a whole bunch of little weak beams together. So you think, well, what good is that? Can I have different amounts of data on them? No, they all carry the same data. But what happens is that then they are focused into a single beam, if you will, to go along the fiber optic cable. But we know that if you take some things here and you focus them down, they don't become suddenly a straight beam. Okay, that's just not how light works. But we can take all of these little elements in a V-cell array, and all of these are like weak little lasers. Focus them down so that together they're kind of sorted together. They're not truly coherent together, but they're kind of sorted together for shorter length multi-mode fiber optic. Now, in the old days, we didn't use V-cells, we used an LED, which was something that would just glow when a current went through it, and it had all sorts of little rays going all over. But we don't use the LEDs so much anymore. We use these V cells instead. Now, if you want to have a stronger single, much more coherent laser, because I mean, in theory, a laser should be coherent light, where all photons move together in lockstep. There is another type, and there are more, and you don't need to memorize this, but just so you understand a bit, there is something called the distributed feedback laser, and what it is that they've got like these notches or these ridges or whatever you want to call them, of this lattice work, and by applying energy to this construction, these things will start to generate photons, but because of the structure, only the photons that are in tune with that structure, that resonate with that structure, are going to kind of like build up, and you keep on giving it more and more energy. And finally, the whole thing bursts through and pew, the light goes out. This is a new design as opposed to the old days of laser where you had like two mirrors. One was more polished than the other, and you just energized it until the light was bouncing back and forth and pew, it went out. Now it's more like we tune it, and you've got some of these that you can like even change the frequency. But because of the structure, it's tuned, and so only the light that fits, only the frequencies that fit this tuning, that resonate with this tuning, are going to become part of the laser, and pew, it all goes out as a coherent beam. So that's what we use for single mode laser, for single mode fiber optics. And if we were to look straight at the output, this is actually a picture of a transceiver, you would see like two lenses, right? One for transmitting and one for receiving. I'm going to talk more about those in just a little bit. So we've talked about sources of light, how the light works, how it travels. Let's talk about the cabling itself. So fiber optic cable, we know that the conductor is a single strand of glass, or in some cases, plastic. And it can be fiberglass too, but you know, it's going to be something that you don't want to have stick in your finger. It will carry pulses of light instead of electrical signals, because light is fast. Light is not subject to electrical or radio frequency or electromagnetic interference. And we use fiber optic cable in LAN backbones and trunk links between switches. Obviously more costly than copper, at least at this point. And you can run fiber optic cable over long distances without having to boost or clean the signal. Now, depending on the kind, you can go to 80 kilometers without boosting the signal. You will need two cables. Fiber optic cable, by its nature, is half duplex. Now, I will show you how to break that rule in a second, but you'll have two cables, two beams of light. One for transmit, one for receive. And you might recall, we were looking at a picture of a transceiver that had a transmit side and a receive side. So that is the idea with fiber optic cable. Here's a picture. So we've got this little tiny core. It's like the thickness of your hair, surrounded by a cladding with a different refractive index. So you're going to have that reflection going on. Surrounded by a coating, surrounded by another coating that basically gives the cable strength, and then an outer jacket to protect everything. Multi-mode fiber optic cable, MMF, comes in 5 varieties. They're all basically increased specifications of each other. They're all OM. That doesn't stand for OMG, right? There's OM 1, 2, 3, 4, 5. And each of these, optical multimode, each of these came about as fiber optics was evolving as a technology. So they have the wider core, and all but one of them have a 50 micron core. So the strand of glass is 50 microns in diameter. The cladding is 125 microns. And when we talk about fiber optic cable, we talk about like, we'll designate it as like 50/125. The wider diameter allows multiple light beams to travel down the cable. It's easier to work with, easier to terminate, but because they're not super coherent together in lockstep, there will be signal distortion the farther down you go, so it's better for shorter distance. The cable types, like I said, OM 1 through 5, so they're cheaper and they're used in LANs. So let's talk about those OMs, right? OM1. Now this is the one that has a slightly larger core, 62.5 micron core. It's legacy. It's for short haul and low bandwidth. OM2, we don't use anymore. It's obsolete. OM3, we'll see a lot of this even today. It's optimized for laser. It's best for data center top of rack or just in between, a switch here and a patch panel there for short distance LANs or storage area networks. OM4 is also laser optimized. You can have it go a little bit longer, be on the campus backbone, high density. It's good for things like medical imaging and high-speed financial transactions. And then OM5 is not in super wide use yet, but it's laser optimized. Data centers that use heavy automation. It's for the fastest speed, but the distance is relatively short. 100 gigabit at 155 meters is a typical application. So here are different MMF applications. Now, it can be very bewildering to choose the right transceiver and the right cable and the right this and the right that. It really revolves around the Ethernet standard. Realize that all fiber optic is to carry Ethernet, okay? At least in the fiber optic we're talking about. So you've got these Ethernet standards. Remember how I talked about 10 base, 100 base, 1000 base? Well, so here we've got 1000 base SX for gigabit speed. You can use OM1, 2, or 3, and you can see the distances on how far you can go. So OM3, being higher quality cable, can go to 1 kilometer. The wavelength, the frequency, the wavelength, which is, like what is the distance between two peaks on the wave, because all electromagnetic energy is an oscillating wave. Well, the wavelength is 850 nanometers. That is in the infrared range, but I'll talk a little bit more about that shortly. You can, like I said, use OM1, 2, 3. You can even use OM4. And the form factor of the transceiver will be SFP. More on transceivers shortly. When we want to have 10 gigabit short range SR, 10G base SR, we can go 10 gigs, but look at kind of the short distance depending upon the OM cable. If you use OM3, that's 300 meters. If you use OM4, it's 400 meters. Still an 850 nanometer laser, and the form factor of the transceiver is SFP+. Then we've got 25G base SR, short range, 25 gigs. We can use OM3 or OM4, but notice how the distance has gone down. Instead of 300 and 400 meters, we're down to 70 and 100. Same wavelength for the laser, and the transceiver is something called an SFP28. I'll show you a picture in a minute. Then we've got ones where you gang them up. We've got quad SFPs. So we can have 40 gigs, 100 gigs, where you basically have a certain connector and it can break out into like groups of 2 or 4. You can see the evolution of all of this. The fastest we can go is 400 gigabits at this moment using OM4 or OM5 at 150 meters distance. This is for multi-mode, okay? Not single mode. And the OM4 will use an 850 nanometer laser, whereas the OM5, you would do the 910 nanometer laser. It's close. And it has specialized form factor for the transceiver. So these are common applications. Do you need to memorize this? Probably not so much, but this is real life stuff, okay? And you would need to understand that the speeds will be like 1, 10, 25, 40, 100, 400. You can break these out also. There are breakout cables I'll show you in a sec. So now we're up to single mode. We've been talking about multi-mode, which is cheaper, shorter distance. Now we can talk about single mode, which is more expensive, longer distance. Multi-mode, as we saw, uses those V-cell arrays, whereas single mode is going to use some other type of laser, which creates a single coherent beam. So in single mode fiber optic, the core is very narrow. So an 8 to 10 micron core with 125 micron cladding, but it's called 9125. So in between 8 and 10, right? A single beam of light will travel through along a single path, one mode. Of course, the light source is laser. It uses its own designation for cabling. It's either called OS1 or OS2. So not OM, OS. And in patch panels, or patch cables rather, single mode fiber optic cable is always yellow. The OMs can be orange, aqua, light green, or sort of a fuchsia color. They have a name for it, something violet. But single mode is always yellow. We use it for LAN backbones, data centers, cable TV, or the phone company will use it. And here is an example of single mode fiber optic cables plugging into patch panel. So OS1 is meant for indoor, 10 kilometer maximum distance. It has 1 decibel per kilometer attenuation. So to give you a sense, 3 decibels is something that's half. So, or depending, if we lost 3 decibels, we're half strength. If we gained 3 decibels, we're double strength. So 1 decibel for every kilometer of distance is how much we'll lose the light, how much the light attenuates. And it's cheaper, not that it's cheap, it's cheaper. OS2 is meant for outdoor. It can go to 200 kilometers max distance. It has 0.4 decibels per kilometer attenuation. It's a lot more expensive. The basic specs, though, of these cables are the same. The difference is the cable quality. And single mode fiber patch cables, like I said, are always yellow, this sort of canary yellow in color. So here are the common single mode applications. These are the Ethernet standards. So we've got long range, we've got long range. I don't know if the ER stands for extra, but it's like a medium. ZR. There's actually SRs as well. I'd like to point out to you, yes, the single mode, 10 gigabits and faster up to 400 gigabits, 10 kilometers or more depending. Notice the wavelength difference. Instead of 850 nanometers, 1310 or 1550. So if you're wondering, gee, is this transceiver single or multi-mode? Look at the wavelength. You know, if it's 13 or 1500, that's single. If it's like 850 or 910, that's multi-mode. And then you can see the various OS cable types here and the form factors for the transceivers, starting with SFP plus and then going from there. We'll see some pictures. We can compare what the cores look like. So this is relatively correct, kind of blown up. Here's an OM1 with a really big core, relative core, the 62.5 micron core, versus the OM2345, which is 50, versus the OS2, which is 9. So you can see, even though the cladding is always 125, the core will be like much bigger, a little bit smaller, and then really, really small. Now, it's very commonplace to take fiber optic cables and bundle them up into backbone cables. Now, they're not always just for backbone use, but like you can bundle up 2 or 8 or 16 strands into a common jacket. And you see this stuff around here? This stuff is a bunch of strands of, I don't know, plastic or something, which basically give it mechanical strength. You can step on it a little bit, push on it, and they'll kind of like move and protect the actual strands of fiber optic cable inside. Now here's an example of a backbone, 4 sets of single mode OS2 in a really thick backbone jacket. So we use it to go in between floors and go up like a cable ladder and other things, because it has the ability to support its own weight. One of the risks of certain kinds of cable, especially fiber optic, is if it doesn't have all this strength, these strength elements, then it can't support its own weight. If like rested on something and like it rests on something here, it can't support its own weight. Or trying to go up a ladder and then you sort of like gently cable tie it down, can't support its own weight. So that's why we have these sort of strengthening elements here. So here are examples of bundled cables for backbones, and in a moment I'm going to show you how to terminate them. So then, one of the things is that our internet is dependent on undersea cables. And the question is, you're not going to put that, single mode backbone cable, you're not going to put that underseas. So what do we have? Well, for submarine communications, it's really interesting. They use a specialized single mode fiber with inline repeaters to boost the signal. I mean, the cable itself carries this. Boost the signal every 100 to 400 kilometers. We are at 12,000 kilometers right now. That's pretty, 6,000 miles, something. Get this, it will carry DC. So in addition to the fiber optics, it's going to have metal that carries 3,000 to 10,000 volts DC down the conductor, and it's close to the core because that's what's going to be used for the repeaters that are built into the cable. And the cable is protected by Kevlar to protect against shark bites. So here's an example of what an underwater, at the bottom of the ocean floor cable would look like. Here's a real picture right here. And here's a real picture of a shark trying to bite one. So anyway, that is what is used for specialized submarine communication cables that are fiber optic. So can we interchange single and multi-mode fiber? Well, you can try, but it's a bad idea because even if the devices support it, you're going to have huge amounts of loss because cable is designed for specific wavelengths. And you'll have signal degradation, you'll have overdriving or overloading the receiver. It's a bad idea. Don't try it. So from end to end, make sure that your cables and your transceivers and your switch ports all match. This includes if you're using backbone cable, patch panels, patch cables. So like in my young days, I made this mistake one time. I allowed us to have single mode fiber between floors, but I wasn't paying attention really to how it was being terminated. It was being terminated into ports, switch ports that only supported multi-mode. So that was my bad. That was dumb. I didn't do enough research. So make sure that everything supports the mode and the type of light and the frequency, or rather the wavelength and everything. So we've talked about fiber optic cable and how the light works. Let's talk about the connectors. These are the most common types of fiber optic connectors you will see. You can use these for both single and multi-mode cable. Any of these. They will work with either, both. Here is the good old SC, the subscriber cable, the stick and click. You'll notice that you can have them in just like one, or you can have them that are in two. And sometimes you can even break them apart. I mean, the connector is designed for them to pop apart. So that's very common. Another one that's super common in data centers is the LC, the local connector, the lock and click. Or there's this kind, the ferrule connector, the FC, which is really meant for like high vibration environments. Then there's the stick and twist, which is very similar to sort of a bayonet connector. Then you have multi-fiber push-on, MPO, which is used when we have these quad transceivers that break out. I'll show you in just a sec. And then there's MTRJ, mechanical transfer register jack, which is for lower speed implementations. I don't know who uses MTRJ very much anymore. So let's say that we have patch panels, and we've got like the server room downstairs, and we've got like distribution patch panels at all the different floors and different wings of the floors. And we're going to run fiber optic cable. We're going to run a bundle in a backbone array. And remember, fiber optic takes 2 strands for every transmission, because you need transmit and receive. So 2 strands for every cable, if you will. How do we terminate? When we run this cable, you pull it and it's like thicker than your thumb. And how do you terminate it? Well, This is where pigtails often come into play. Pigtails are a way to terminate the many strands of a backbone cable to a patch panel. So pigtails can be SMF or MMF, single or multi-mode, and it's basically just a short strand that already has a connector at one end and the other end is just raw, doesn't have anything on it. You splice each strand of the backbone. So the backbone comes in and it's got like 24 strands or 12 strands or whatever strands, and you separate them all out and you splice a pigtail to each one. And then the other end of the pigtail you plug into the patch panel, or some of them the pigtail is already in the patch panel, but usually you just plug them into like pre-cut holes. So you splice these together. You can either use an electric arc, what we call fusion splicing, or you can do a mechanical splice with epoxy. The connector is connected to a pass-through on the patch panel, and we usually get pigtails in these bundles. So let me kind of show you how it works. Here's a bundle of pigtails. What are these, 8? Something like that. You can see the connectors are already on. What you don't see is the raw end down here. Here's one where this is a very classic sort of fiber optic patch panel. There are little holes cut, and you can plug these things. Sometimes these will have the little connector right here, a pass-through connector. You plug these in. So each of these, you plug them in, plug. In order to sort of like manage all of those strands, there's usually like what we call a cassette. And it's just like either 2 reels or 1 reel, and just kind of wind it gently around, put a little top on it, and that keeps the cabling from just like being crazy and being at risk of being damaged. So you've got this cassette here. And then what you do is you, as you splice these, here's a little splicing thing here. It's really cool. You like watching a little window right here, and you clamp down that little inky dinky, pigtail and the one strand from the backbone, and it will automatically line them up and then flash, like with a little electrical arc that like melts them together, fuses them together. So it's pretty cool. And you got to do that for every strand with every pigtail. Well, so what you do is when you're doing this, before you do any of the fusing, you take the backbone cable and you bring it in. It's usually in the back or even on the side, but usually the back. And there's some strain relief, so it like clamps down and it holds that in place, so there's no strain. And then you like pop the top off of this cassette, and the pigtails and all the extra stuff just kind of winds around in there. And you fuse every one of them, you close it all down, you maybe cover it with something. And that is how you terminate it. And now you've got this patch panel, and you take each of these little things off and you plug in some kind of patch cable. So what do we plug into the switch? Now we know that the fiber optic patch panels will have just passive pass-through connectors. But switches don't have fiber optic connectors. They'll have on their ports just like a little square hole, and you have to plug something into that. Well, the thing you plug in is called a transceiver. So a transceiver is an adapter. It lets you plug different kinds of cable into the same empty switch port. So it's the interface between the cable and the port. Cable types, there are several different types of cable that use transceivers. Fiber optic, obviously, but also DAC and twinax, we saw a picture. And even twisted pair can use a transceiver, because the port itself doesn't care what the media is so much. It cares about the speed and the duplex and that kind of thing. And then the transceiver handles things like the media, and it handles the wavelengths and frequencies and dimensions and of whatever we're plugging into it. Most transceivers are some variant of the old SFP, the small form factor pluggable, although that is being phased out in favor of SFP+. Then you have a patch cable that plugs into the transceiver. Now, some types of cables already have the transceiver built on and you can't take it off, but not all of them. So in fact, there's such an array to choose from. You not only have flexibility, you can get totally confused. Here's an example of a transceiver plugging into one of the switch ports. And you can see these switch ports are just like, they're not exactly empty holes. You plug something in and there's something that connects on the back side, but you can plug all kinds of things into these, all kinds of transceivers. So here's an example of a direct attach cable. There's twin X as the cable, and the transceiver is already built on. I mean, the whole thing came like that. In fact, I have an example right here I want to show you guys. So this is a DAC cable. I use these all the time. I remember showing this and somebody was like, is that fiber optic? No, it's twin X cable. And then these DAC transceivers in front, you just boop, plug it in. It's really fantastic. So when I look at this, this thing tells me it is a Cisco 10G. Okay, SFP plus. And I can hardly read it, but it's 10G. And this is probably 5 meters or less. Okay, so there's one. You can also have the RJ45 twisted pair type connectors that are also on a transceiver. Let me see if I have one here to show you guys. Here is an example, like you're seeing on the screen, of a direct attach cable. The cable itself is actually twin X, and then it has built onto it an SFP plus transceiver. And so I've got a close-up picture here. So it's 10G SFP plus, and I can just use this. It's not fiber optic, but I can use it when I need a short length 10G connection. Or you can even have these RJ45s, and like I've got examples right here. So here's an RJ45, and I can plug twisted pair right into it. Boop. Okay. Well, so how do these then plug into the switch? And sometimes they take a little doing to unplug. Well, okay, so I have here a module for a Cisco switch. It's an older module, but it works just fine. And it's got 4 switch ports on it. Now, here's an RJ45. I also have an SFP plus for fiber optics, and then I had that DAC cable. So I can, in these ports, I can just like plug one and then another. If I look in there, there's like a little connector in there. So I can plug this, if I'm doing it right, just go boop. Okay, so that particular one will take a fiber optic cable. And then this one here, if I do this right, think, that will take a twisted pair cable. And then I can take my DAC, which has a built-in SFP, and I can plug that in and do it right. Boop. So you can have different media types because the ports, so long as they're 10 gig or 1 gig or whatever they're supposed to be, or 10.1 or whatever, then the media type's not that important, so long as you have the right transceiver. So direct attach cable and twisted pair, they can use transceivers, and then of course fiber optic can as well. Fiber optic transceivers come in a dizzying array of form factors and types. You might have one form factor, in fact you will have one form factor that supports all kinds of Ethernet standards. Most of them are bidirectional. They've got the little transmit and the receive. There are a few that are just single directional, but most of them are full duplex with both the transmit and the receive. So like I said, most of them have a transmit and a receive side. Now the transmit side, and this part is really important, the transmit side is where you will see the light. The receive side, of course, won't receive any light. So when you have the transceiver and you've got a cable, you look in the transceiver, and it's not really a good idea to look straight in because this is laser light, but it's low power, so I'm not suggesting you do. I'm just saying people do it a lot. You glance in there, you turn off all the lights, you turn the lights way down, you glance and you can barely see a faint red light, okay? Now, yes, it's infrared, but the infrared will not be strictly a single frequency, okay? It will have some slop on either side. I mean, whenever you generate any kind of radiant energy, you're always going to have harmonics. So it's not going to be like one frequency, it's going to be like a curve like this. So your eye is able to see the little bit of red that is sort of on the outside of that spectrum. So I have resorted to, gee, I wonder if we're even getting transmit through here. Turn the lights down, take a look. Oh yeah, I can see a little tiny red light. Or hold something white up against it and see if you see the little bit of red right there. Or there's an even cooler way to do this. You can use your phone's camera to see the light, okay? Because some infrared energy is going to pass through the filters of your camera, the red, green, blue filters, and it will show as a white light, even though it's not truly white. So this is kind of like what it would look like. You use your phone, and you got the camera pointed at it. When you see that glow up, yep, that's transmit, it's working. So you can even see it on the cable, and you can see it coming out of the transceiver side. And when you look at transceivers with a little latch on top, the transmit is on the left-hand side. If it's upside down, because some ports, they're like mirrored like this, then it'll be the opposite. But when you look at it with the little, like here, see the little latch right here? When you're looking at it this way, the transmit's going to be on the right, or excuse me, on the left-hand side. So using the phone is a really cool trick to protecting your eye and seeing if you've got transmit or not. So here is the classic small form factor pluggable SFP. I mean, we've had it forever. It actually, you know, the old fiber optic connectors were these big things called GBICs, and then they got smaller, and this is called the mini GBIC. Now we're pretty much based around this form factor or some variant. We use it, of course, for data. It supports gigabit Ethernet, fiber channel, SONET, other things that use fiber optic light. It replaced the old big fat GBICs. I hope you don't ever have to see a GBIC in your life. Sometimes people call them mini GBICs, and they also are going the way of the dinosaur. We are using SFP pluses these days. They can go up to 4.25 gigabits per second at 150 kilometers distance. Now here's the one we use the most, the SFP Plus, the enhanced form factor pluggable. So this is an enhanced version of SFP, duh. 10 gigabits, 80 kilometers, not compatible with SFPs. So you might find yourself actually trying to plug in the wrong kind into a switch port. Now, knowing what you know, look at this. Look closely at this label here. Yes, it says it's a class 1 laser, meaning it's a low power laser. 10G, 1310 nanometers, 10 kilometers. Is this for a single mode or multi-mode fiber? Can't hear you. 13 nanometers, single mode. You get 850 or you're below 1,000, multi-mode. You're above 1,000, single mode. So this is a single mode transceiver. While connectors don't care if it's single or multi-mode, transceivers and cable do. Now here is an idea that actually this is really cool. The quad small form factor pluggable QSFP, you have a wider connector, a wider transceiver with a breakout cable. So you can have one here, and then it breaks out to like 4 individual ones, QSFP. So you have these double fiber pairs, can be single or multi-mode for Ethernet, fiber channel, InfiniBand. Man, who still does InfiniBand? That's got to be long gone. And SONET. Compact, hot pluggable. That's what I love about these things. These SFPs, they're hot pluggable. And a single big fat one will break out into 4 1 gigabit lanes. Now, let me show you a big fat one as an example here. This isn't exactly the same cable type. This is actually a quad SFP DAC, but you can see how it's like really big as opposed to, say, one of these. Well, here's another one. Here's one. In fact, this is a really good choice. I can pull this off, pull the little rubber thing off, and when you look, that is where we would plug in the cable, and we would actually plug in MPO cable, multi-push on. And so here's a QSF, but this one is actually a QSFP Plus, which is the next thing we're going to see. The enhanced QSFP, with a little MPO connector right here. And I just pulled the little rubber thing off. So this is the modern version of the QSFP, 1 by 40 gigabit link or 4 by 10 gigabit lanes. So what I've done in data centers is, because the good switches have these ports, you plug it in and then you break it out. You don't necessarily need 40 gigabits. Well, you might want 40 gigabits from one rack to another, or you might want 10 gigabits going to different devices on the same rack. So that's what that QSFP Plus is all about. Pretty cool. And you can use it to connect switches, routers, host bus adapters for like SANs. And we use them in data centers all the time for high performance computing. Here's an example of the Quad SFP Plus with the MPO push-on connector with LC breakouts for LC breakouts. So this thing takes 40 gigs, but it breaks out into 4 10 gigs. Here's one where the transceivers are pre-attached. So it came with the transceivers. You don't have to like buy the breakout cable. Here's an example of an oldie but goodie that I dearly love working with. This is the Cisco Nexus 3172 PQ switch. You can see it has 48 RJ45 pairs or RJ45 ports, but it also has 6 Quad SFP Plus ports for uplinks. I love working with these. Here's the QSFP28, the Quad SFP28 hot pluggable. They all are. For 100 gigabit data, you can break it out to a single 100 gigabit or 2 by 50 or 4 by 25, your choice. Here's a 400G optical transceiver, and you can zoom in and you can actually see it talks about that. High speed for high performance computing environments, top of rack, leaf spine, which we talk about elsewhere. You can have 200 Gs. Yeah, it's the G force, man. 200 gig breakouts, 4 by 100 or 8 by 50. And then finally, we have the BX SFP. Now, remember how I told you that any fiber optic cable is going to have 2 cables, one for transmit, one for receive. And I even showed you how to look and see which one is transmit, which one's receive, and if you're actually seeing anything. Well, there is the BX SFP that has only one cable, 2 different light waves, one for transmit, one for receive. They both go down the same cable. They both go in and out of the same lens, if you will. It's not half duplex, it is full duplex because 2 different frequencies. Transmit is at 1310 nanometers, receive is at 1550. Oh, wait, quick. Is this single mode or multi-mode? Single mode, because it's over 1,000, 1310, yeah, that's right. So this BX SFP special single mode transceiver. And why would you use it? Well, I don't know. Single mode fiber, 1 strand, full duplex, bidirectional, transmits, receives at the same time. And you can see, wow, if you were ever curious about what the actual frequency is for these wavelengths, because there's a direct relationship between the length of a wave and the frequency of oscillation, 1310 nanometers, 228.849 terahertz. Okay, don't need to memorize that. It's just sometimes I geek out. Uses an LC connector, 1, not a dual pair, just 1. So how do you select the right transceiver? It is really easy to get confused, okay? I mean, it really is. It's bewildering. Start with the Ethernet standard. Remember how I said it's, 10G something, right? Look at the Ethernet standard. I showed you tables of MMF and SMF Ethernet standards. Do the switch port, the transceiver, and the cable all support the same standard? That's your first thing. Check compatibility. Not all switch ports will use just any old generic transceiver. Some of them will say, you better use the ones we create just to make sure it works. Well, it's not always true, but they want to make sure that you buy their stuff, right? You might have to match the fiber type. Don't go using multi-mode OM something for a single mode transceiver. even though you might have the right kind of connector. No, it's not designed for it. So make sure that you're using the proper multi-mode fiber or single mode fiber for the transceiver's wavelength. Also, understand your distance requirements. If you need to get across campus, you're not going to use MMF. You're going to use single mode. So select the transceiver that supports the required distance. Usually distance is not something the switch port cares about, okay? It cares about, and it doesn't even care about frequency, single, multi, it doesn't care about that. That's the transceiver's job. It cares about, is this gigabit or 10 gigabit Ethernet, or 40 gigabit or 100 gigabit? That's what it cares about, okay? So the switch usually cares about speed and duplex. It doesn't care so much about distance or frequency or cable type. You may have situations where you have to be backward compatible. This has got to be 10 and 1 gigabit. So make sure that the port and the cable can support that. Can it toggle between 1, 10, 40, 100, or whatever? Continuing, consider what we call the power budget. Now, this is something that we study in other types of classes, but switches only have so much power. Even though I said that a switch does not care if this is single mode, multi-mode, the type of laser that is used will use a whole lot more power or less power, okay? So you've got to be mindful of that. Yeah, the port doesn't care if it's single or multi-mode, but if you're going to put in a long-distance cable with a high-power single-mode transceiver, that might be more than that port can actually give you. So you've got to make sure that the switch port's optical power budget, the amount of power it can give the transceiver, is something that it can give you that you need. Like, you know, don't use some switch that can only give you X when you need 5X. So that's something you're going to have to look at the specifications a lot more. Check for environmental factors because, like I said, some cabling, not all cable is made the same. Some of it is meant for harsh environments, industrial environments, outdoor environments, meant to support its own weight, going up a cable ladder or going across or whatever. So make sure that the transceiver and the cabling can support the environment you're going to be in. So like if you're in an industrial environment, you know, manufacturing floor or Internet of Things, something, you know, you're out on a factory floor, you're going to have like more temperatures and who knows what the humidity is going to be like. And if you're outdoors, you're going to have lots of humidity issues. And so you got to make sure that you're using the cabling that is suitable for that. And it's more of a cabling issue, but make sure then if the cabling has certain types of connectors that the transceiver also can support those connectors. And then of course, duplex and connector type. So is it going to be duplex? What kind of connector? Most SFPs are LC. But I mean, who knows? You might have a quad that's an MPO. And then, of course, you might have requirements, like in a high-performance data center environment, where you need a transceiver that has really low latency and really good signal integrity. So you need to make sure that the specs, you know, it's just like, yeah, okay, this is 10 gig, but it has more latency or the signal's not as good. So you need to check all of these things. Finally, let's talk about media converters. A media converter is not a transceiver. It just connects one type of cable to another, and it's going to be for Ethernet. Fiber optic to twisted pair RJ45 is the most common way we do this, the most common implementation. So don't confuse a media converter with a transceiver. Transceivers are used to plug cables into switch ports. Media converters change cable types. So like I've got one right here. They usually take like 5 or 9 volts. A little power supply. This one here has a twisted pair, and then it has fiber optic right here. I've even got some examples here. So like I've got, here, let me just make sure these are together okay. I can plug these in here, see if I've got them the correct way. Okay, so if I'm doing it correctly, just plug this in like so. Okay, and then that's the fiber optic side. And then for the twisted pair side, I'll plug in this one. You'll very commonly have a need for these when you're connecting. Okay, so see, I've connected in that way. You'll very commonly have a need for these, especially like if a telco brings in a fiber optic line and you don't have fiber optic connections on your switches, you use a media converter. So it's not going to change the speed of anything. It's not going to change the duplex. It's just, in this case, fiber optic to twisted pair. So that is a media converter. And usually they take a little bit of power as well. They're usually not passive devices. Finally, let's talk about storage area network connectivity. And it seems funny to just put SANs right here, but this is in the context of all of these cable types and connectors and transceivers, because storage area networks, you've got your array of disks with a controller, they'll use this same stuff to connect to switches and servers in same rack, different rack, couple racks down the hall, something like that. SAN usually will use one of three protocols for connectivity between the disk array and everybody else. You can use plain old Ethernet, just plain old Ethernet with twisted pair, Cat5e or faster, DAC twin AX with an SFP, or single or multi-mode fiber with a variety of different transceivers we've already looked at. General purpose LAN-WAN networking, good old Ethernet is one of the protocols that storage area network can use to connect to the servers. Then there's fiber channel, which is its own protocol, and it was carried directly on fiber optic cable, or sometimes twin AX, could be single or multi-mode, with either quad SFPs, SFP plus, or a specialized SFP called the fiber channel FC SFP. And so a lot of SANs did this, and it was quite expensive because it was highly specialized just for that. And then a much cheaper version is to have iSCSI. Now, once upon a time, there was something called SCSI, and SCSI was faster for connecting to disks. It was a signaling protocol for connecting disks to motherboards, right? Operating systems. And we would have like these big wide SCSI cables and connectors and cables and stuff. If you had an old Mac Plus, you had a big old fat SCSI cable on the back, and then you could connect different things by SCSI cable. Well, SCSI still exists, small computer system interface, and there is something called iSCSI, which is sending SCSI commands as payloads of IP. Actually, TCP port 3260 to be exact. We would typically use the same kind of cabling for Ethernet. It's very common to do like iSCSI SAN, like I've had a lot of net apps where you hook up iSCSI and you hook them up just using DAC cables with twin AX, 10G DAC cables with an SFP plus type transceiver. So these are the different ways that storage area networks would connect. They've got three different protocols for talking to the network, and we use the same cabling and transceivers and stuff and such that we were talking about when we were talking about fiber optic and SFP and those things. So let's review what we know. IEEE 802.3 Ethernet is a standard specifying cable type and speeds for coax, twisted pair copper, and fiber optic cables up to 400 gigabits per second. Unshielded twisted pair is the most popular network cable used around the world. It's inexpensive, it's easy to install. It has an IEEE recommended max distance of 100 meters, primarily used in Ethernet LANs. Shielded twisted pair is like UTP, but wraps the wire pairs, either all of them or as pairs, in a conducting shield to reduce the risk of electromagnetic interference. Shielded twisted pair, STP, is good for areas of higher RFI EMI, but not completely impervious. Don't Don't pull it for your hospital radiology department. Shielded twisted pair, STP, is thicker and more expensive than UTP. You should probably memorize these particular standards. Cat5e at gigabit, Cat6, 10 gigabit, but only at 55 meters, 6A, full 10 gigabits, 100 meter, especially good for cameras, IP cameras, and wireless access points. In fact, if you have to make a recommendation, and I in real life have made this recommendation, Cat6A, or you might find yourself in a scenario where you have to do it. 7 up to 10 gigs was for SCTP for 100 meters, and 8, 40 gigs short distance twisted pair, 5 to 30 meters. Plenum is a cable classification based on fire safety. It's based on what the outer jacket of the cable is made of. It's not like the cable itself, but it's like how fire safe is this? Does it give off toxic fumes if it burns? Plenum grade cable, plenum or non-plenum, the designation will apply to twisted pair, coax, fiber optic cable. Plenum grade does not give off toxic smoke when burned, so you put it in plenum air spaces like air ducts or hole return ceilings where the air goes back into the central air conditioning unit. Non-plenum grade cable uses standard PVC insulation. It will give off toxic fumes when burned. It's meant for non-plenum areas like walls and floors, or just being on the floor. Direct attach copper DAC is a type of network cable. It's a whole assembly that you buy complete. It supports Ethernet speeds up to 100 gigabits, typically uses twinax for short distance cabling, and it's factory terminated with one of these transceiver modules, SFP+, quad SFP+, quad SFP28, something like that at both ends. Or if it's a quad, it'll have a breakout. DAC is a lower priced alternative to fiber optic cabling, and I've used it a lot and it's great. Twinax, twin axial cable, is coax, but it has 2 inner wires that are twisted around each other instead of a single core. It's the most common cable type for DAC. Registered Jack 11, RJ11, is what we use for landlines, landline telephone lines. It has 4 pins, but only 2 wires are used. RJ45 is found on pretty much all twisted pair cables, whether unshielded or shielded. It has 8 pins, 4 of which are used for sending and receiving, a pair for transmit, a pair for receive. Here is the wiring, the 568B wiring. Memorize this. From pin 1 to pin 8, white, orange, orange, white, green, blue, white, blue, green, white, brown, brown. For when we do crossed wiring, we will take 568B on one side and A on the other, where the orange pair and the green pair will be swapped in terms of pin position. F-type is a coax RF connector used for TV and cable modems. F connectors push on, and then you screw the little outer nut on to hold it in place. BNC, bayonet Neil Conselman, is also used to terminate coax cable. It has that quick twist and lock design. It's used for antennas, analog CCTV cameras, professional video broadcasting, and test instruments. Fiber optic cable carries light instead of electrical signals. It's commonly found in LAN backbones and trunk links between switches. It can run over very long distances without having to boost or clean the signal. Depending on the type, you could go 200 kilometers without amplification, without boosting. And I think I said earlier, we're up to 12,000 kilometers, but when I looked, we're actually up to 39,000 kilometer underwater cables, fiber optic cables that have like 10,000 volts DC along with the cores and wiring with built-in repeaters, 39,000 kilometers, because they have built-in repeaters and they have that high voltage with Kevlar to protect them from shark bites. Fiber optic cable is more costly than copper cable, And you need two cables, two beams of light for a two-way full duplex transmission, unless you're using a BX connector. You have one cable for transmit and one for receive. Multimode fiber optic cable has a 50 micron core with 125 micron cladding, and that's how we specify fiber optic cable. We'll say it's 5125 or 9125. The cladding is always the same, it's just the core that's going to be different. Multimode fiber optic uses LEDs or V-cell laser arrays, and pretty much the LEDs are gone now, but that's the light source, the V-cell laser array. The cabling has a wider diameter core, which allows the uncoordinated multiple rays of light to travel on the cable. It can go for a maximum 2 kilometers, and it's used in LANs. Single mode fiber, SMF, has a much narrower core, 8 to 10 microns, but we designate it as 9, with the 125 micron cladding. It uses a much more highly directional laser as its light source, so it's all coherent. One beam of light travels through a single path. It can go 200 kilometers unrepeated. It's used in LAN backbones, telcos, and cable TV. Don't mix SMF and MMF along the same path. You're going to be sorry. Fiber optic connector types are SC, stick and click, LC, lock and click, ST, stick and twist, MPO, multi-fiber push-on, which is what we use in the quad SFPs, and MTRJ, mechanical transfer register jack. A transceiver is an adapter that lets you plug different types of cable into the same empty switch port. It is used for several cable types, including single and multi-mode fiber, twin-ax, and twisted pair. Fiber optic transceivers come in all types of Ethernet standards, form factors, single and multi-mode, and cable type support. When selecting a transceiver type, ensure that the switch port, the transceiver, and the cable itself all support the same requirements. A media converter is a standalone device that connects one cable type to another. Fiber optic to twisted pair is the most common type of media converter. Storage area networks, where you've got a bunch of disks over here that connect to a bunch of servers or switches, they have 3 protocol types, just plain old Ethernet, fiber channel, or iSCSI. Those 3 protocol types can go on all those different kinds of cabling and connectors and transceivers that we were just talking about for twisted pair, twin-ax, or fiber optic. And that, my friends, is our look at wired transmission media. And I don't know about you, but I need something to drink. No, not that kind of drink, just some tea or something. So I'll see you in the next topic.